Um, Welcome to the eighth lecture on this NSM course on OpenACC. We looked at various constructs in OpenACC, and yesterday we looked at specifically vector operations and various aspects that we encounter while dealing with vector operations. Today we are going to go two-dimensional, and we'll look at some of the matrix operations and what caveats come into picture and what we should be aware of while dealing with matrix operations. And whatever we have studied so far, we'll try to apply that in an interactive way for matrix operations. So one of the most important matrix operations is matrix multiplication. And we would like to see if we can parallelize these. Once we are able to parallelize these matrix operations, matrix multiplication, then with a good chance we'll be able to parallelize other aspects also. So depending upon how much time we have, we'll go through the other matrix related applications, but we'll be focusing more on the matrix multiplication for the most part of this lecture. Okay. So the method essentially goes over the row of the first matrix and the column of the other matrix, and does some of the multiplications of these corresponding elements, and then writes it at the appropriate place in the final matrix. So that is essentially C equal to A into B matrix multiplication. Right. So one of the, A matrix has a row major axis. In that sense, we are going from 1 to 2, whereas B matrix has a column major axis, and that matters a lot when we are dealing with cache memory accesses corresponding to matrix multiplication program. So there has been a lot of work which tries to improve these memory accesses, and one of the most powerful techniques in this context is tiling, where instead of going over the whole row and whole column of A and B matrices, we tile it into small chunks such that we go over those again in a similar manner, but hopefully the tile size is small enough that it will fit into the cache, and therefore we don't have to incur a lot of penalty, because if you optimize the memory accesses or caching for row major, that is for A matrix, that may not be suitable for B, and vice versa. So tiling is kind of trying to get a middle point between the two by reducing the matrix size to a tile and just working on that tile. So one tile from A, one tile from B, and you compute all this information and put it into the appropriate tiles element into the matrix C, right? And then you try to repeat that, keeping, let's say, A tile the same, but changing the B tile, and then go on producing intermediate results, right? And these results need to be accumulated into the C matrix from different tiles, because what I get as one value from just a tile may not be the final value in C's cell. So it has to be repeated across other tiles also. Even from parallelization perspective, whatever I was telling is also applicable in the sequential context. Even in the parallelization perspective, tiling becomes important. You can perform lots of these operations in parallel, lots of these multiplications definitely in parallel. And as far as sum is concerned, you can either perform some sequentially or using some sort of hierarchical divide and conquer manner as a reduction. Or you can as well use atomic instructions to write the final value, assuming that you have already enough work to be done such that that atomic cost doesn't turn out to be very crucial. Okay, so the basic implementation of matrix multiplication, as we all know, runs in 3 nested loops, and let's say I, J, K, and then we try to compute that information for C's each cell using the rows of A and columns of B. And in our code setup, if you go to matmult.c, you'll be able to find this code, but we'll again use this code to, I'll show the basic codes on the slides, and whatever is the remaining associated code, which I'm not able to fit onto the screen, you can take a look at it in the actual code file itself. So before we go to the developing this matrix multiplication in OpenACC, one small homework exercise which you can think about is that once you have developed this for two matrices. Maybe you can try optimizing it for multiple matrices. There are reasons why one wants to do that, and the reason being that not always going from M1, M2 to then M3 and then M4 is useful. We know that matrix multiplication is associative, and therefore you might be able to do M3, M4 first, then M1, M2, and then the results of these might be combined. So the order in which you come up with for the matrix multiplication will start mattering depending upon, I mean, and the amount of work that you do also starts mattering, because the dimensions of these intermediate matrices will go on changing. So how to find out the most optimal order, that is anyway NP hard, that is it requires exponential number of checks to be made or exponential number of operations to be done. But nonetheless, there are heuristics which try to some extent, help. Although not optimal answer, it tries to improve the execution time for multiple matrix multiplication. So you might want to, those who are interested might want to try that out. Some of you might actually require it in the context of your research. So I strongly recommend looking at, first develop a basic matrix multiplication and then do look at how to optimize it for multiple matrices.
Sir, one minute thing, can we just go back?
Yeah.
So this, as it looks like M1 into M2 into M3, this is very familiar to our normal product. And the thing is, you have written it like this, but it will be a function, right, matmult. So I think we cannot potentially have a reduction like this, like whatever we write for and have a reduction, we cannot have that. That is one thing, right?
Reduction you are saying here?
Yeah. So what I was saying is, initially we know that the multiplication can have a reduction, right? If it is a normal multiplication.
Correct.
But then if it is a function like matmult a comma b, that cannot be having a reduction, right?
That is true. Well, true and false, I'll say. The reason being that from the discussion that we had about reduction, yes, it cannot be put in a similar format. However, if we say that matrix multiplication is associative, and can we try to reduce it in some...
Yeah, I get that one. So you will be having like multiple multiplications being done asynchronously, right?
That is correct, yes.
Okay. As you know, in C++, we can do a operator overloading, right?
Right.
So can we actually overload the multiplication operator and then put it in the reduction? You get me what I'm trying to say?
Yeah, so at the OpenACC level, it is not supported yet. I mean, OpenACC does have C++ support, but the user-defined reductions are currently not supported. So although we can say that star is overloaded, but that is only syntactic sugar until the compiler finds out what that star is. But yeah, currently it is not supported. Hopefully in a newer version, it will be supported for arbitrary functions. So we'll be able to say mult M1 comma M2, and then on top of that, we can say mult this mult comma M3. So that we should be able to do.
Okay.
Currently, it won't be possible.
Okay.
Yeah. Any other concerns, questions so far?
Yeah, just a comment. I guess this matrix chain multiplication using dynamic programming, maybe order of n-cube algorithm is known. It need not be NP-hard problem, I guess.
Oh, is it? Oh, I see. Okay, my apologies for that.
No. I'm just curious to comment.
Yeah, maybe. Yeah, I'm mistaking then. If the optimal order is in terms of the minimum number of operations to be done,
right. The order in which
dynamic programming. Yeah, you are right. There is a dynamic programming solution for this. Yeah, thanks for correcting me, Rama. You are right. So yeah, actually that's then it leads to a good point that since there is an optimal answer possible, can we implement that in OpenACC to get parallelism also benefits into this?
Very nice, actually. Both solutions people do independently. The theory community work on this kind of matrix chain multiplication, and the other side now,
right.
Parallel setting together will be very good.
That's right. So just for the classes introduction, Rama is a faculty member from IIT Tirupati who works on a blend of theory and practice. So he has done his PhD on the theoretical side of computer science, and he has developed interest on the systems side. And he's also amongst us today. So I think it's very good that he is here so that I could correct this part. My apologies for saying that this is NP hard problem. It's you are right that it can be solved in a dynamic programming. Good. All right. So yeah. So let's look at the basic sequential version, which is just 3 loops. Ijk, and then somehow that C of ij I can initialize just before k loop begins, and then C of ij plus equal to aik into bkj, right? So that is our usual C code, sequential code corresponding to this. And how do we parallelize it? Well, we just add a pragma and boom, that's it. I mean, as far as acceleration is concerned, you can still achieve it, just compile the program, run it, and it will give you hopefully the correct answer and so on. But then this is only the beginning, right? So we would like to optimize it as much as possible. So there are 2 parts to this particular code. One is, of course, the actual matrix multiplication, but when you look at the overall program, you realize that there is initialization also. In this case, Cij is getting initialized here, but A and B need to be initialized. So, and why that is important from the perspective of OpenACC is because you can parallelize those also, right? So that parallelism I can also bring in by adding similar pragma there, where now there is a nested loop compared to what we had in vectorization vectors, where we had a single loop. So let's say some initialization I am doing. In this case, it's just I plus j, but it can be any arbitrary initialization. So this sounds fine so far as a naive parallelization. So what are the places where you will do the optimized parallelization now? Any suggestions? So we would like to apply all our learning in this course to parallelize matrix multiplication. So I need your suggestions on how to go about it.
Sir, we can copy in A and B and only copy out C.
Okay. So Pranshu says that one aspect is to add a data clause in which we copy in A and B and copy out only C. And that we will do, let's say inside main or some other function which is calling this initialization as well as this matrix multiplication. Right? So that is one way in which this can be made better. Okay. Any other suggestions?
Why do we suddenly have this CIIJJ0 there?
Not suddenly. I mean, you can always initialize it there, or you can initialize it outside. Either way is fine.
No, but if we don't have that, we can use the collapse 3 nicely, right?
Very good. So that's another observation, which I'll talk about that. But yes, as Dhruva is suggesting, if you do not have this C of ij statement here, then you essentially have this for I, for j, and inside that directly for k. Right? So it's more like a normalized or standard form. And then if you have this, then we can use a collapse on all 3. Currently, the collapse is possible only for these ions. Right? So we'll come to that part soon, but that's a very good observation. Good. Okay, so that is second one. What are the other suggestions?
Again, I think we will, this will be in some sort of a main, so we will have some data clause. So I think this init mult can be done using some present.
Right. So that is another observation, that since we'll have the data clause where we are just copying in A and B, and that initialization is for two matrices A and B. So you would like to specify that it is already present so that the compiler doesn't have to worry about even checking if it is already present or not. Generate code corresponding to that. So we can specify present mat here, and that will be helpful. Okay, any other suggestions? The other suggestion which was revealed by Dhruva collapse 3 suggestion is that you can actually give a collapse clause here as well as here, right? And in this case, it is going to be collapse 2. Yeah, so that is also going to be helpful for our discussion.
Sir, I was just looking up some OpenACC documentation. So in some examples on the internet, I have seen that along with this parallel loop and whatever, they are actually mentioning the key clauses gang in the pragma description. What are those about?
So I think the gang, when we specify the vector length, yeah, even the compiler, when it gives the output, it shows gang comma whatever vector length 128 or something. I initially thought that it is something which is required. Before you specify the vector length, you have to specify some sort of a gang there. But that doesn't seem to be the case. You can specify vector length even otherwise. So I'm not sure why that gang is appearing there. I mean, I have tried it specifying and not specifying, it still works out. And the configuration remains the same. So I'm not really sure why that gang needs to be specified.
So, sorry, your answer is meant for parallel reason or parallel loop?
Parallel loop. So we can specify, yeah, we can specify gang comma, let's say vector length of 128, right? So even if we don't specify gang and just specify vector length of 128, the same configuration happens.
This is for parallel loop, right?
Parallel loop. Are you asking Dhruva?
No, I actually saw this in some OpenACC documentation. Sir has not mentioned this.
No, but I am just guessing those extra parameters for gang and all that. Typically, for parallel reason, it is mandatory, right? Because in a parallel reason, we just mention whatever the reason available, how many threads are getting executed, that code that we are specifying in the pragma statement. No, that is in the parallel reason.
Right. So num gangs is something which we specify. Right. Gang is a keyword which I think Dhruva was asking.
Okay. Sorry. Okay.
Yeah. So that.
Yeah. So if you.
Yeah. Go ahead.
No, I was saying that not num gangs. It is just gang. This is just gang. Keyword. No number is following that. Correct. If you give num gang, you have to give some number.
That is correct. So yeah. So even that's what I was mentioning, that in the compiler output also you will see this hash pragma ACC parallel loop gang comma vector length 128. This is what is likely to appear by default. And yeah, even if you remove that and just give vector length, it doesn't change the configuration. So I have not understood the meaning of that. It might just be the default which appears. That could be the reason that it's optional to be given. Yeah, if somebody finds out the reason why that gang needs to be given, please feel free to post it on the group. All right. So, okay, so we had some suggestions with respect to the data clause, collapse clause, as well as present one. And yeah, so let's do that one by one.
Reduction also possibly for the innermost loop.
Right. So this C of ij plus equal to, this is a possibility for a reduction, and therefore we might be able to use even the reduce clause, or if you want atomic instruction, either way should be possible for the adding to C of ij. That is also a correct observation. Okay, so yeah, let's go one by one into optimizing this code. I'm going to add some collapsing clauses. So we should be able to add collapse 2 easily. And that is the question that with Dhruva observation came in, that if I want to collapse all of ijk, because maybe I have relatively smaller value of n, and in that case, even if I collapse ikj, I might still have reasonable number of threads running this particular loop. So can I collapse ijk? Currently you cannot, because of this statement. It has to be in a standard form, that is j should be immediately inside I, and after this for j there should not be any other statement inside for loop of I. In a similar manner, for loop of j should not have two statements, like in this case there is a Cij assignment and then there is a for loop. It should have directly for k. If this pattern is observed, then there is a possibility of applying collapse 3, which I can do by removing that C of ij there, and then I can apply collapse 3 here. Now the question is, where do you do the initialization to C? Initialization to C can be actually done outside. The way I am initializing A and B, you can as well initialize C again in parallel, and that can take care of this Cij equal to 0. That is one. The second thing is this collapse 3 really useful? So what do you think? So correctness wise, there may not be any issue, but performance wise, collapse 3 in general is likely to be useful if you have values of n to be relatively limited. But in this case, even if the value of n is relatively small, parallelizing this k loop may not be a good idea. And the reason being that if we parallelize this loop, then n threads which are running this k loop are actually going to write to C of ij. They are going to both read and write to C of ij. Right? For a particular pair ij, all the k iterations are going to run in parallel. That means there are n threads which are going to be available for one ij pair, and therefore C of ij is going to get read and written to by n threads which are running in parallel. This is a kind of reason for requiring a synchronization in this case. So there is a data race essentially, which thankfully the compiler figures out and adds appropriate clauses here such that either reduction happens or there is atomic assignment happening there and so on. However, because of that synchronization, the cost of writing to CFIJ is higher than the amount of parallelism that we get by parallelizing this k loop. So although technically it is very easy to just change it to collapse from collapse 2 to collapse 3, you have to be careful that whether there is a synchronization that is getting involved, and the synchronization might not be even known to you. And that is also the downside of high-level parallel programming, that you might not know what all is the effect of just changing one small parameter. Right? I hope I have made this point clear, that you have to be careful in doing collapse 3 here. It may not give you the benefit. In general, it is likely to give you benefit if this would have been, let's say, ijk, three-dimensional matrix equal to A of ijk into B of ijk, something like that, where it is completely parallel. Then collapsing 3 loops is likely to be beneficial. But these collapse 3 may not be as beneficial as we think it would have been. Okay. Okay. So although it turns out that there will be some benefit, out of this parallelization. The reason being that I am also doing this multiplication. This multiplication can happen in parallel for all these n threads which are essentially running for this k. So there will be some benefit and then there will be some cost. It so happens that the cost outweighs the benefits that we receive by this parallelization in this particular example, and therefore it might be better to be satisfied with collapse 2. Any questions so far? All right. So like it is easy to probably commit performance related mistakes, it's also easy to correct it in OpenACC. So we can change it. Okay. So let's come to the other suggestion that how about the data transfer? We have not really talked about it. So let's go to Pranshu's suggestion that can we have optimized data transfer. That will require us to look at the calls to this. So let's come to main, where I might have these clauses where, as Pranshu suggested, we can have create a B and copy out C. In addition, we can also say create C, and that is going to be helpful to us because C needs to be created anyway for writing to C of ij. And I have initialization of A and B to some values, let's say I plus j. But I also need to initialize C, so I can use some function which just zeroes out all the values of C. And then I call mult, and all of this is nicely there inside this pragma. So any questions so far? All of this looks familiar, I suppose. Okay, so once we have this, the next question that I can ask is this all? And that leads to Dibajyothi's next suggestion that when we have this data clause, we need to be also taking advantage of this by telling the compiler, don't worry about the data being copied or checking that the data is present or not. Yes, it is present, and therefore I can go to initialization and the matrix multiplication functions and specify the present clauses there along with, let's say, the collapse clause. In giving the present clause, again, we have to be a little more careful. You can either specify it like this. If n is a hash defined, most probably this will work out. There won't be any issues. But in case n is not a hash defined constant, you might have to specify this as part of the present clause. Otherwise, it might just end up copying one word of this matrix, and you might not even understand what is happening, but there might be suddenly wrong output which might come, or there might be a sec fault on the GPU, and you might see just zero values or garbage values in C of ij or mat of ij. So you have to be a little careful about that part, because if it copies only one word and you start writing to all the other words, then there will be a sec fault on the GPU, and that might not be caught, and you might not be given that information in the output that there was actually an invalid memory location, invalid memory access. So it's better to be safe, especially yeah. Go ahead.
Sir, anyway, since we are doing in the multiplication loop, we are doing collapse too. We can move this zero function out, right? We can actually initialize zero in the k loop, like if kk equals to 0, in that way.
Yes, that is also possible. So C of ij inside the k loop you are saying. That is possible.
Oh, no.
Okay. Yeah, so
maybe I got confused. Sorry. Yeah.
Okay, sure. No problem. But I'll just anyway say that if kk equal to 0, then C of ij equal to 0, and then C of ij plus equal to A of ik into bkj. That is possible to be done. It's just that that additional if condition is going to be there in the innermost loop, which is not a good idea, because that if condition is going to get evaluated n number of times for the innermost loop, although it is going to be useful only for the kk equal to 0. But anyway, that's correctness wise there won't be any issue, only the performance will get hit. All right. So yeah, so this part seems to be okay. I hope you guys are with me so far. So essentially what we are doing is developing from our original sequential code. How do we go on adding these OpenACC pragmas to make it more and more interesting? Okay. So another optimization which comes in, and that is useful not only in the GPU case but also in the CPU case, this can I not access it in a different way? I mean, ijk loops, is it possible to rearrange those such that I access them in, let's say, ikj order or some other order? Is it possible to do that? So it turns out that yes, you can do that, right? So you can reorder the loops, and especially on the CPU, you will realize that this IKJ loop, a loop structure, is going to be more beneficial than the usual IJK. Right? The caching effects are going to be much better because the order in which these loops appear is also the order in which the indices appear. When we had IJK, it was good for IJ and IK, but it was not so good for KJ because the J was kind of the parent loop of K, whereas the way row major access goes, K followed by J is going to be, J is changing faster, but J is in the outer loop in the original case. Now when I have IKJ, that follows, so I is a parent of J or grandparent of J, which satisfies this because of the row major order, that for each I go over J. J is changing faster, and that is how the loop is. In IK also the same thing is followed, and in KJ also the same thing follows. So on CPU, on sequential CPU execution, this is likely to be very useful, and the caching effects will help you improve the execution time in the IKJ order. So do try it out whenever you do matrix multiplication. Instead of the usual textbook solution of IJK, try out IKJ. But on the GPU, that may not be the case. The reason being essentially the parallelism. Even in the context of CPU, when we are doing in parallel on a multi-core setup, this particular ordering may or may not give you the benefits. And caching effects is one thing, but the synchronization requirement might turn out to be another, especially when you have such a collapse to loop. Right? So therefore, we have to be a little careful about this IKJ order in the context of GPUs. So what I'm going to do is that I'm going to show all these different variations of the course, and in the end, I'm going to summarize the performance of all these different variations for matrix multiplication to give you some glimpse of which optimizations kind of worked out for the matrix size that I have tried. Right? So I have tried it for matrix size of 5 cross 12 cross 5 cross 12, 512 cross 512. So let's see if this turns out to be beneficial. Right? Okay, so if I have this IJK versus IKJ, which one should we optimize for? Should we optimize for a row major order? Should we optimize for column major order? This is the usual notion that comes in. And if you have a usual code like this, then it always becomes a problem, because once you try to optimize for one, the other matrix goes for a toss. Either C and A will get benefited, or C and B will get benefited, and the third one will be left out. So we cannot do something directly. We'll have to get into this sort of a tiling, which allows both of these to coexist such that they both are in the caches. The tile completely fits into the cache, and then we are able to perform operations a little faster. But that works out for matrix multiplication because this accumulation is possible. C of ij is essentially plus equal to. So you can go on accumulating these values inside C by splitting the overall matrix into tiles. If you have some other operation which is also accumulative, you can apply the tiling concept there. But there might be some function which you might have some arbitrary function of AIK and BKJ and writing it to CIJ. If that operation is not accumulative, then you cannot use tile. In fact, you will get a wrong answer if it is not an accumulative operation. In some sense, this is called as, I think this is called as a distributive property. If that is satisfied, then you will be able to distribute it using tiling. Otherwise, you might get a wrong answer if it's not a distributive property. Okay? But it so happens that most of the times, the kind of operations that we do, plus and star, these are distributive operations, and therefore we will be able to perform this easily in the context of parallel execution also, as far as tiling is concerned. Okay, so let's understand a little bit about tiling. So it gives kind of the joint advantages of the row measure and column measure accesses. And typically on the CPU, it gets influenced by the cache line size. But on the GPU also, it is important. But it's not as important as, let's say, the parallelism benefits, right? So the reason being that the number of threads which are running on the GPU is typically a very large number, right? So if you have, let's say, n as the data size, the total number of threads might be n or a small factor of n, right? And when you have a very large number of threads, the amount of cache that every thread gets is going to be relatively small. And therefore, the caching benefits will not be that high as much as on the CPU, where you have just a few tens of threads. And therefore, the caching benefits out of tiling may not be that substantial, but nonetheless, you might get some advantage by tiling over not doing anything with respect to, let's say, even if you don't do collapse, then tiling is likely to be helpful. And just to show pictorially how the tiling works, so I have taken this image from Michael Busman's paper. So you have the overall matrix. Let's say this is matrix A, this is matrix B, and C is getting computed. I am going over ith row of A and jth column of B, and then writing to this particular orange location, which is going to be the let's say second row and second column, which is what I am accessing here. So instead, if I go in this particular order, then that is going to be not beneficial for this particular matrix, because there will be a cache miss all the time. So what I do is I divide this matrix into small chunks, and if these small chunks fit into the cache, then I can do the computation for all of these elements and all of these elements together, right? So there are multiple rows here and multiple columns here, and all of those get accommodated as a partial sum. So this first row and this first column, then the then the first row and the second column, then the first row and third column, all of these are in the cache itself. And since all the elements are in the cache, all of these operations for one tile can get completed as far as writing to this particular memory location is concerned. As far as only the only the green ones is talking about this part, but I can essentially write about all of these orange bars as a partial sum with respect to this tile from A and this tile from B. Right? So that I can accumulate, and then when I go to the next tile, let's say this one, then I can continue to have this tile, then I can go to this tile for B and then accumulate that sum into the second row and second column. So I can accumulate that again into the same matrix, the same tile of C, and note that when I go to the next tile of A or maybe next tile of B, I can still maintain the same tile for C, right? So I can go on doing that accumulation as much as possible, and then go to the next row of next tile row of A or next tile row of B, and so on, right? So this is how the benefits of caching will come into picture. How do you implement this, right? So anybody has seen a tiled matrix multiplication code? How will it look like structurally? Okay, let me ask you the question in a slightly different way. Okay, Jess says 4 nested loops. Okay. Yeah, so from Jesh's answer, let me ask you in this manner. Maximum how many nested loops you have had in any of your codes so far? Maximum how many nested loops you have had in your code so far? Swapnil says 6. Okay, so it's almost like a 6-dimensional space that Swapnil was working in. Any other suggestions? Himanshu says 3. He is with me. I have not gone beyond 3. Rajanya also is 3. Right. So we all are on the same page. Swapnil is in a different space. Okay. So, okay. So just out of curiosity, Swapnil, what application was that? ML chipset compiler. Oh man, that's an interesting one. Okay, sure. So thanks for that. It turns out that as far as styling is concerned, since we have to convert this original matrix into tiles, which are going to have the x and y axis, we'll have to add 2 more loops to our regular 3 nested loops, and therefore we will get a 5 nested loop structure, which is going to have 2 loops for the tiles x and y directions, and then 3 for the ikj or ijk. And writing that is not really difficult. You will find that code online. Plus, I think it is there in matmul.c or matmul2.c, one of them. So that tile code you can have. It turns out that OpenACC developers probably found this very common because many people will deal with matrix operations, and therefore they have provided a keyword, thankfully, to take care of this. Right. So that keyword is a type, and you specify prior to your loops, and you specify which indices you want that tile to be made of, and internally the code that gets developed, that code that gets generated is essentially 2 loops per index that is specified here. So for I there will be 2 indices, for j there will be 2 indices, and then for k is going to be there. So therefore there will be this 5 nested loop which gets automatically generated for us. Thankfully we don't have to write it, but even if you write it, I think that will be interesting. So this particular tile method is not restricted to matrix multiplication. You can do it for even other simple matrix related operations also. You can just try it out and hopefully it will give some benefits. But as I was mentioning, it is going to be less beneficial compared to the amount of parallelization that you can get, and therefore you might not see as much benefit on an accelerator because of this. But if you are generating code for CPU using even OpenACC, you might want to try using tile and see if you are getting any good benefits. Likely that you will see large benefits out of this. Okay. All right, so that sounds good. Let's come to the summarizing part of these various techniques, and I want to show you briefly how these different techniques perform on my accelerator. So for timing, there were multiple options. As I was mentioning, you can use a clock method, or you can use this PGI environment variable, which you can set to get the times, as I had showed on one of the slides. But then to get, I mean, the PGI compiler, PGI runtime is going to give you the times only for the parts that are happening on the GPU. But there are some parts, some bookkeeping that also needs to be done from the CPU side, which doesn't get counted when you use that PGI environment variable. So using that, we'll get relative times of different kernels easily, or different functions easily. But if you want to time it as an application, then you should use something on the CPU side. Right? For example, just to give you a glimpse of that, the PGI compiler might say 25 microseconds and or maybe 200 microseconds for something which, if you time it on the CPU side for the same function, which is getting converted into a GPU which has a pragma and so on, it might have actually 600 milliseconds as the overall time, right? So the overheads that CPU side might have are going to be much larger just to bookkeep this information. So you should not get misled by that PGI time. although that is correct, you are finally interested in the performance of your application, and therefore you should probably use get time of day the way I have done in this particular exercise. All right, so let's look at these line by line. So on left hand side we have these different techniques, and right hand side is matrix multiplication for input size of 512. If I have just the parallel clause without any data clause, then I get 434 milliseconds as the total time for matrix multiplication. If I add data as well as collapse clause, collapse 2 in this case, then that reduces a little bit to 430. What does that mean? That means that when I did not have the data clause, the amount of data that was actually getting transferred automatically was actually similar to what I would have otherwise given as the data clause. Right? So this is a little surprising, and unless you have large number of large arrays to get I mean where the non-optimal data transfer is happening, then only we will get benefit out of this data clause. If the compiler, I mean that's what I mentioned in one of the discussions, that the compiler seems to be quite intelligent with respect to many aspects of I mean this OpenACC compiler has been quite good as far as my knowledge of compiler goes. There were a couple of times when we found surprises, but then there was a logical reason behind it, right? So that way the compiler is doing a good job here. So you might want to try out if really the data clause is really giving you any benefit or not. I mean, in this case, these are statistically, this difference is statistically insignificant, right? So this is just 1% difference or so. If you add data as well as time instead of collapse, right? So I did not add collapse, but I might add time. In that case, there was a significant improvement. So in this case, it so happened that the caching benefits turned out to be high, and that's a good sign. And therefore, not always though the tiling will give benefits. If you are using collapse, then tile might interfere with that, and the compiler may not allow you to do collapse as well as tile together, unless you are doing it for two different pairs, right? So collapse you are doing it for ij, whereas tiling you are doing for kw and so on. Then it is okay. But otherwise, for the same loop, you should not be doing collapse and tile. You won't be able to. So in this case, we got large benefits because of this tile. So you might want to experiment with that further. Changing the launch configuration of the kernels, for example, numgangs gets decided by whatever is the problem size, and then there is a default vector length, right? So the default vector length turns out to be 128 in my installation of OpenACC, which is likely to be the case in your installation also. But in case it is different, the number of gangs is going to get calculated appropriately. But then I can specify it using numgang. So let's say that instead of whatever is coming out to be the numgangs, I specify it as 128 without using tiling, right? So over collapse, if I use numgangs, then my timing changes from 430 to 303. And with some changes to vector length, it also remains around the same time. This indicates that changing the launch configuration might turn, I mean, you might have to tune the launch configuration to suit your application and the problem size. And it can give relatively significant benefits. And don't take these as only for matrix operations, right? So for example, this tiling was applicable only for matrices, but maybe you are using vectors or some other operations where you might not be able to use collapse, but you will still be able to use numgangs and vector length specifying on the pragma, and that can easily give you some performance benefit. So please try that out. Collapse 3 over collapse 2. Okay, so I'm not sure if this collapse 3 is just after collapse 2, because what I recall was that collapse 3 was not really significantly changing. Maybe I made some mistake. I probably had some of these also there, and then I added collapse 3. I'll have to look it up. So please ignore this collapse 3 line. Instead of ijk loops, if I use ikj and continue to have collapse 2, does that change the performance? Yes, it changes the performance to some extent, and I can have around 307 milliseconds for performing this matrix multiplication. If I use ikj and then tile it, now for tiling I cannot use ij because for tiling these need to be consecutive, and therefore I have to use tile ik, and that doesn't really change too much of performance. It almost remains the same as far as this is concerned. So yeah, that is one. Another aspect that I tried to, okay, there is concern here. Can you put in the CPU serial and CPU parallel execution time when you post the slides? CPU serial and CPU parallel execution. Sure, I'll do that. So I'll have to add the CPU serial and CPU parallel execution times. Sure. Yeah. So another thing which I did is that instead of putting all of this into different functions which require, well, there is just a function call, but is it possible that I can have all of these inside main? And when you put it inside main, there is some advantage that you can have. For example, the initialization of A, B, C you can do in the same loop. I didn't do that as such. I kept these separately so that there is a fair comparison. And it turned out that there was some small improvement in the execution time compared to, let's say, one of these, let's say around 300 or so was the original. And when I put everything, then there was a small improvement in performance with respect to that. That has turned out to be the lowest currently, but that also takes away the benefits of good programming practices. That is, we should have these codes separated out in different functions, right? So that's usually a good programming practice. So you might have to pay some small penalty because of that. The last one, out of my curiosity, I did was the kernels clause, where I just had the sequential code and I just put the kernels clause above it. Everything was in main, by the way, and I checked if the matrix multiplication should be parallelized nicely or not by the compiler. It turned out that the timing was not really bad, right? So although originally it was 291 with all my clauses, data, parallel, present, etc., all that added, collapse, etc. And then when I did kernels, it gave me 303 milliseconds. Now that is really quite kind of encouraging, because that means that the compiler is able to find out the dependencies well. By the way, the code was also correct. I mean, the output was correct as far as I checked a specific value in the matrix. I didn't check the complete matrix multiplication. But as long as that value is recurring in the output, I felt that it was correct code. So that kernels was actually doing a good job with respect to matrix multiplication. And this also is an indication that if your codes are nicely data parallel, then the compiler can really help you there. Right? So even if you do a nice parallelization using just kernels, it might turn out to be reasonably close to what you can achieve. Of course, if you increase n and beyond 512, there is a good chance that this difference in performance might go on increasing. The hand optimized version versus whatever compiler does, there might be the difference might go on increasing. But nonetheless, there is a good start just by doing kernels. If I am able to get all of this, that's really very good. That's also one of the important reasons why I say that the compiler is actually, OpenACC compiler is written very well. All right, so this was kind of a summary of what performance benefits we got out of all these exercises with respect to matrix multiplication example. Since we have a few minutes, I'll spend some time on the red-black processing. There is also one sort of a numerical method which some of you might have come across, where there is a stencil computation. What is a stencil computation? That means that you have some sort of a 2D matrix or a 3D matrix, And then in different iterations, you are performing different operations on these cells. So the values in these cells, in these 2D or 3D matrix, are going to go on changing based on a function of its neighbors. So the cell in 2D will have, let's say, 8 neighbors, or including itself, it might have 9 neighbors. Right? Similarly, in a 3D space, there might be 27 neighbors, including itself. So all of these neighbors are going to be affecting the value of this cell in the next iteration. What is an iteration? It's just a different time step. So you are simulating some sort of time step function across these different iterations, and every time step there is some function which you will apply. This function is going to depend upon your physics, your biology, your chemistry, and from parallelization perspective, it doesn't matter what this is. All of these can be cast as nice stencil computations. And it's not always necessary that these neighbors should be only one hop away. That is, if you are talking about row number I and column number j, that is cell ij, then only I minus 1 and j minus 1, or I plus 1, j plus 1, all of these are only going to come into picture. In general, you can have I plus k, I minus k coming into picture as neighbors. But still, all of these can be nicely cast as stencil computations. And one of such stencil computations leads to something called as red-black processing. So stencil computation with special dependence. Special meaning it does not have any arbitrary dependence, just from a few neighbors, right? So that turns out to be very specialized form of dependence. In this case, I am just showing it as a of ij is in 2D is dependent on some function of a of ij itself. I have given plus equal to, so that a of ij is kind of included. This plus may not be plus. I mean, this plus is overloaded, so you might have some arbitrary function there. Or maybe I should just write a of ij equal to f of a of ij, and then I minus 1j, I j minus 1, I j plus 1, and I plus 1j. 4 neighbors of this particular aspect, right? So for this particular set. So I'm not using, so I think I'll just show pictorially, right? So if I talk about ij as a red cell, then that is going to depend upon a of ij itself, and then I minus 1j. So that is previous row and the same column, which is the black one. And then these 4 black ones are the ones that are going to appear here, right? So a red cell is going to depend upon these 4 blacks. And if you talk about a black cell, that is going to depend upon these 4 reds, right, as its neighbors, and so on. So you can actually cast this particular style of processing, which actually appears in some applications, as 2 parallel loops, right? In one parallel loop, you write only to the black cells, and in the other parallel loop, you write only to the red cells. Right? And you repeat this processing, and that gives rise to essentially time step stencil computation for this red-black processing. Right? As a homework exercise, you can try generalizing it to more than k colors, but essentially you are going to have those many sequential loops, right? Sequential steps. Each step is parallel. Right? So in this case, it is red-black. In the other case, it might be red, black, blue, and so on. This code is also available. You might want to take a look at it. But okay, maybe let me just open it up. I'll have to, I think, reshare the slide. Let me just unshare, then reshare this. Okay, so I hope this code is visible to you guys. Can somebody confirm that it is visible?
Yes, visible. Yeah.
Thanks. So the main, let's come to this part first. Main contains some matrix, and then there is a diff which needs to be calculated every iteration so that we go up to a certain threshold. That threshold is kind of specified as 10 to the power minus 4 or so. What we do is there is some initialization of the matrix, and then there is a do while loop until either the diff becomes lower than epsilon or the number of iterations go beyond certain threshold, right? So currently that I have committed out, it's for only a fixed number of iterations, but anyway, you can change it. What internally it is doing is just calling this particular function. What does this red black do? As we were saying, there are two for loops which are sequentially executed, that is one after another. Each for loop is essentially going over the matrix, so there is II and JJ iterations, and similarly for the second loop. Within that, there is some computation happening, right? So if it is red, that is II plus JJ mod 2 equals 0, then you do something. Otherwise, if it is black, say, then you do something else, right? So in both cases, the operation turns out to be very similar. It's just that the entries that I might be using might turn out to be a little different, or the processing that I might do might also differ, right? So in this case, it's not really changing anything with respect to that, but this is a standard template for doing the red-black processing, right? So the actual computation is not so much important, whether I'm doing here 0.25 or 0.1 or something, that is not very important. The important part is that there is dependence on these different kinds of sets, right? So the red depends upon the black, black depends upon the red. The access also turns out to be the same, so you can actually merge these two. But for the sake of understanding this red-black, where the functions might be actually different, I have kept those separate. Once I have this particular code, how do I go about parallelizing? Well, one thing is that definitely you can have parallelize these loops here, right? And then there is, as far as processing is concerned, these two loops are nicely parallel. So as soon as you get into 2D, the collapse also comes into picture, or tile also comes into picture. So that is one part. One small aspect that comes into picture is this diff. This diff is a kind of global variable, right? Because it is outside the for loops, and therefore we have to be, either we add some sort of a synchronization, or if the compiler is intelligent, then hopefully it will add some reduce clause or atomic clause corresponding to this diff. So that is one point which we have to worry about. And then the usual data clause is going to come into picture here, where before initialization I start the data clause, and it spans all of this initialization as well as the do while loop. And using that, I can perform the usual optimizations of only creating or if the initialization is happening on the CPU, in this case it's nicely parallel, so it's okay. But in case it is happening on the CPU, maybe I'm reading the matrix out of a file, then after this initialization, I can do a copy in of A, and then at the end, I can possibly do copy out of A in case I'm interested in finding out the final matrix and so on. So those are the kind of, so there is a red-black 2.c also, which should give this parallelization constructs, which I'll skip in the interest of time. But yeah, that is what essentially what I wanted to kind of convey. So I'll stop here, and if there are any questions, we can take those up now.
This solution, what we have just discussed, one can implement using two arrays naturally, right? In case if we do not have this thought about red-black dependencies, then the other natural one is using two arrays, right?
Very good observation. So what Rama is suggesting is that since there is reading as well as writing involved here, there is a data race possible, right? Sorry. Here, because of plus equal to, there is a data race happening because I am reading as well as writing to A of ij. As long as I am parallelizing it correctly, then there won't be any problem. But then I am also reading this A of I minus 1j, and which the other thread might be writing to, and that's why we have to separate these two out. Okay. So now So to avoid this, we have separated these two in time, right? So we said that there are 4 conditions for data arrays: more than one threads, that is at least 2 threads, same memory location, simultaneous execution, and at least one of them should be a write. And one of the ways in which this data arrays can be avoided is that we dissatisfy at least one of these properties. So the way it is satisfied in this code is that we separated the writes to the common memory location in time. Right? So there is no simultaneous execution writing to the same memory location. Another way in which this can be done is that can I convert these writes and can I separate these reads and writes? So essentially, if I have a copy of this matrix, I can just read from the original matrix and write only to the new matrix. In that case, your reads are going to be not affecting anything because it's a read-only matrix. So multiple threads can read from the same memory location, and at the same time, you are not writing to that memory location because you are writing to a different matrix altogether. And therefore, you will be able to parallelize it very nicely, where where you can afford to have a separate copy of this matrix. In fact, some of you, those of you who will probably be writing simulations, if you can afford a matrix copy, then you will most probably be alternating between these two matrix copies across different iterations. In the 0th iteration, there is an input matrix and then there is an output matrix. In 1th iteration, the input matrix becomes the output matrix and the vice versa. And then that gets flipped again in iteration number 2. So this repeated input-output exchange of matrices can turn out to be very handy if you can afford it. The disadvantage is, of course, that you require twice the memory. And that's why I have been saying that if you can afford it. But yes, if you can afford it, your amount of parallelism can increase. Because the one matrix is totally read-only and the other matrix is completely parallel. That is, all of these IJs are getting read by only one thread at a time. And therefore, the parallelism goes on increasing. You don't really require these 2 steps as such. There will be a single step. Good. Any other concerns, suggestions?
In one of the previous slide, when you mentioned about this special case about all in main, the running time was somewhere around 291 and 291 milliseconds.
Right.
They just want to confirm that the overheads are just for function calls, right? Is that correct?
Yeah, I checked that, and it turns out that the overheads are only for the function call. So around 9 to 10 milliseconds, we were getting advantage.
Right.
So that seems a little surprising to me. But then it's possible that, although I was not running anything else on that machine at that time, so that I checked. But I don't know, that needs probably a further closer inspection. But that was surprising.
Okay. And another one, that inner loop one can try to apply reduction, right?
Yes.
The innermost loop.
The innermost loop
variant.
multiplication.
That could be another variant, right?
Yes, the innermost loop, we can apply a reduction, or if we do not apply, that is, we parallelize the innermost loop also. My guess is that the compiler will automatically find that it is amenable for reduction and generate code for it. But if not, we have to add that pragma. You are right. That will be another parallelism benefit that is possible. Swapnil says we should be able to offload inner loops only to GPU and execute outer loops on CPU. Will this perform differently versus all offloaded to GPU and vice versa? Okay, so there is another way in which sometimes you might want to parallelize. For example, keep the outer loop for the CPU and keep the inner loop for the GPU. That is one possibility. Alternatively, what we have done in the context of metric multiplication is that the 2 outer loops, I and J, we have parallelized on GPU, and K we have kept as sequential on the GPU. Right? There was nothing which the CPU was really involved in. But in case of time step simulations, like the one that I am showing here, in case of red black. This outer loop is a do-while loop, so that we would like to keep on the CPU as much as possible, because there are usually some bookkeepings that I might want to do, or some decisions that I want to do, whether to invoke another kernel and so on. And therefore, these do-while loops are not really amenable for a good parallelization on the GPU. So you might want to keep this outermost loop on the GPU, but the inner loops, the for loops essentially, or do loops in Fortran, you would like to execute on the GPU. Will there be some benefit with respect to parallelizing the outermost loops versus the inner loops on the GPU versus CPU? Yes, in general, that is true. That you will get, I mean, there will be some performance difference anyway, but the idea here is that the GPU should also have some work to do. It should not happen that you have, let's say, n square number of threads because of the matrix computation, and then each GPU kernel is just doing one or two number crunching operations. If that happens, the overheads of launching the kernel might outweigh the benefits. Therefore, there should be some small amount of code which should be there inside the kernel also. That essentially gets done in case of matrix multiplication when you have that for loop, for k loop. Without that, there is essentially a multiplication and maybe a couple of additions that we are doing inside the kernel. That may not be very conducive towards the overall parallelization benefits. So that is one point I wanted to make. The other point is that even if, let's say, the I loop we parallelize on the CPU and keep, let's say, J loop, and maybe there is a K loop also which is nicely parallel on the GPU, that might still be okay. But if you are anyway going to get benefits out of J and K loops, and you feel that I loop is parallel, you better move that I loop onto the GPU, because if it is nicely data parallel operation, you might want to invoke the kernel with even n cube number of threads. Right? So that is usually a good benefit, unless the data size becomes very large or the number of threads becomes very large. Right? So I would recommend that as many parallel loops you would try to offload to the GPU. If there are synchronization issues, then you will have to offload or maybe come back to the CPU side. Or if the number of threads goes too high, then you have to parallelize, let's say, I loop on the CPU side and then J and K on the GPU, or IJ on the GPU and K loop being sequential on the inside the GPU kernel. Swapnil is asking, is there any compiler that provides benefits of parallel execution that involves CPU, GPU, DSP all together for present day SoCs? OpenACC is CPU plus GPU. Yeah, there should be OpenCL compilers which should be able to give you these benefits. And I think some of the OpenCL implementations do work for DSPs also. I think there is some work happening to generate code from OpenACC for FPGAs. So that might give you some benefits, although I have not tried, and I also don't know if it is directly available right now in a working condition. Yeah, that is what I know. But yeah, there will be some OpenCL compilers which should be able to give you. So OpenCL is definitely little ahead of OpenACC. So my feeling is that there should be OpenCL backend for DSPs as well. Sure. Any other concerns, questions? Swapnil says probably we need to modify sample programs. They do not run with GCC. Oh, I see. No, I have not really tested these with GCC. Yeah, maybe in the next offering when I try for this FOpenACC with GCC option, I think I'll execute these programs first, try it out, and hopefully I'll have to change many of these programs. You're right. All right, so I don't see any further questions. So we'll stop here. Tomorrow we are going to look at the final aspects of this particular OpenACC, where we look at again one specific application. In case we finish that application soon, then we'll look at maybe a couple of applications. But yeah, so we'll apply it to a slightly different domain in case of ciphers. Although it's not going to be very different from what we have seen so far, but I'll see what all we could do with respect to maybe even other applications, and then we'll wrap up the course. On Saturday we have the exam. It will be at the same times, same time, 5 o'clock. So you all can join in this particular session, and in the session I will share the link to the Google form which will have the exam, and that you can write, and we'll have a discussion just after the exam. From 6 to 6:30 we'll have a discussion. All right, see you. I'll stop here.
Yeah, just a minute. For matrix and vector also, do we have some kind of tiling approaches?
For matrix, yes, but for vector, no.
No, matrix. I mean, instead of matrix operation, matrix vector.
Oh, I see. So some sort of matrix and vector operation. Yes, that is possible. See, as far as the tiling is concerned, we can apply it to any nested loop as such.
Right.
So if you have the ij loops which are going over the matrix, which is internally performing some operation for the vector also, I think it should be possible to apply. Just that a small catch we'll have to worry about is that the two loops should be in a standard format. Typically in the vector, if it so happens that there is some initialization to the vector or some other processing, there might be J loop as well as some other statement which is related to the vector. If that happens, then it will forbid, but if not, then it should be possible to apply tiling. So it will get applied only to the processing which is involving I and J together. So if it is for the A matrix, if it is for the matrix, hopefully it will get some benefit. But if it is for the vector, I am not sure if it will, how will it really tile it? But then the code should make use of both I and J somehow for accessing the vector. So whatever is the index that is coming into picture, that to that it is going to get applied. So if it is using only I index or only the J index, only that entry is going to be brought into considering that as a small tile. So it's essentially going to be a single index from the vector.
Right.
Okay. So the compiler doesn't know anything about whether we are using it for the matrix or not. So whatever data we are accessing, it's just going to do it for that particular data access.
Right.
Okay, Dhruva is saying, is there any library which is already having GPU accelerated for BLAS operations? Typical one I use is GSL, which doesn't seem to have. So you are talking about specifically OpenACC or even OpenCL or CUDA is okay?
Things which I can call during my in a program. So it will be probably OpenACC or something like that.
Mm-hmm.
So things like I have SAXP and all that in presenting GSL, right?
That's correct. I think, yeah. So there are some libraries which NVIDIA has put forth, and more support is coming for further operations. I don't know one for specifically, I don't know the name, but I just know that there exist OpenACC accelerated libraries which NVIDIA has suggested on their web page. In addition, there are some research works which try to develop some libraries, but the support may not be very good.
Yeah, I think there is something called CU BLAS and all that, right? That is written in CUDA.
That is for CUDA, yeah.
Yeah, so I'm asking like something which I can call directly from an OpenACC program.
Yeah, I think there is. I'll have to look up. There is definitely OpenACC related BLAS operation library available. I'll look it up and let you. I'll just note it down. Sure. Any other concerns, questions?
No, then extension of the same question for the popular data structures, right? In the CPU setting, we have STLs. And even I'm not sure in the GPU setting, few research papers are there, but I'm not sure plug and play kind of data structures like STL, whether we have or not in CUDA setting, and as well as possibly for OpenACC.
Yeah, the OpenACC is actually far behind CUDA, so we
definitely
don't have those. To some extent, Thrust and Cub help us in the context of CUDA. Yeah, as Josh has also written. So that can give you some vector and set, but beyond that, yes, we don't have really libraries beyond the research works currently.
Okay.
Yeah. So I understand that from that angle, you are probably suggesting that maybe there may not be enough support for BLAS operations. But
no, I'm having a little larger question. If that is not there, is it worthwhile to work on such kind of projects?
So yeah, I think that's a larger question. I may not be able to.
Anyway, we'll take it offline. Yeah, sure.
Yeah, sure. Yeah, Suro has given some suggestion with respect to a library. Thanks, Suro. All right. So if there are no further questions, then we'll stop here and we'll meet tomorrow.